Now in this video lecture we will understand these zeolites, right? These zeolites, we call them as shape selective catalysis, right? We'll see why, in a while we'll see why we call zeolites as shape selective catalysis, right? Shape selective is important to understand in this, right? So first thing we'll look at it, these zeolites. Zeolites are aluminosilicates, right? Aluminosilicates which are stones, right? These are aluminosilicates, right, which are stones. So zeolites are stones with general formula this, right, where this M represents your metal cation, M represents metal cation, which may be sodium, potassium or calcium, right? Generally or usually these metal cations are sodium, potassium or calcium, right? And this N, this is X upon N, right? N is charge on metal cation, right? And this Z represents the number of water molecules associated with this aluminosilicate, right? Z is the number of water molecules that are associated with this silicate. We call this water as water of hydration, and this is water of hydration, right? So N represents the number of, the Z represents the number of water molecules, right? So first thing we'll understand that what does the word zeolite mean. The word zeolite literally means boiling stone, right, in Greek language, right? So why do we call it as boiling stone? Let's see this. This zeolite has a microporous structure, right, which has small pores, right, on its surface, or small cavities or pores on its structure. And these pores, when they have water trapped in these pores, right, you can trap water, these water molecules are trapped in the pores, right, on the surface of these silicates. And when these silicate, which is a stone, when zeolite stone is heated, these water molecules or the water in the pores of these aluminium silicates will start boiling, right? That is why we call it as boiling stone, right? We call it as boiling stone because the water molecules which are trapped in the pores, these water molecules which are trapped in the pores of these aluminosilicates will start boiling when this zeolite stone is heated, right? Now these aluminosilicates or zeolites have honeycomb-like structure, right? Honeycomb is, you know, that honeycomb which is built by honey bees, right? Bees, and these bees will store their pollen and honey in this honeycomb, right? And we know that honeycomb will it will look like this. You can look this in your book also, right? It will look like this, right? This is how these aluminosilicates will look like, right? They have these kind of it's kind of network, right, which will look like this. It's like this, right? So it's a honeycomb like structure. We call it as honeycomb like structure, right? So these zeolites have honeycomb like structure. These are three-dimensional network silicates, right, in which some of the silicon atoms are replaced by aluminium atoms, giving ALOSI framework, right? You have ALOSI framework. These are in this honeycomb structure. You have this ALOSI framework, right, in this honeycomb structure, right? So these are three-dimensional. Structure is three-dimensional network silicates, right? These are three-dimensional network silicates in which some of the silicon atoms are replaced by aluminium atoms to form these structures, these ALOSI framework, right? Some silicon atoms are replaced by aluminium atoms, right? Now the most important thing about these zeolites are, since we are studying catalysis and we are saying that these are shape selective catalysis, right? So if you want to use these zeolites as catalysis, right, so first thing that we need to do in order to use these zeolites as catalysis, that we should remove these water molecules, right? So in order to use as catalyst, right, water needs to be removed, and we see that in the general formula it has these water molecules, right? So you heat this zeolite in vacuum to remove these water molecules, right? To remove water molecules, you heat it in vacuum, right? So when you heat it in vacuum, it will become porous, right? It will become porous. Why? Because the structures, this aluminosilicate, the structure of aluminosilicate have pores, right, on the structure, on the surface of this aluminosilicate, in which we have water, right? Onto this, in these pores, these aluminosilicates have water trapped, right? So when you heat this aluminosilicate, the water trapped on the surface will get removed, right? So you have these, and now these cavities or these pores will become empty, right? So now you have cavities on the surface of these aluminosilicates from which water has been removed, right? Now these cavities would be used to absorb the water, to absorb the reactant molecules, right? Which the reactant molecules that will use zeolites as catalysts, right? So I'll repeat. In order to use these aluminosilicates as catalyst, the first thing you need to do is you need to remove this water molecules, right, from the pores which are on the surface of these zeolites. So when you remove these pores, right, which are on the surface of aluminosilicates, the aluminosilicate will become porous, right? Now it has empty cavities, it has cavities from which water is removed. These cavities are on the surface of this aluminosilicate, right? Now the reactant molecules, right, that uses these silicates or these zeolites as catalyst, the reactant molecules will get adsorbed onto these pores, right? Now these pores or these cavities, the cavities or these pores have a size, right? They have a size range that ranges from 260 pm to 740 pm, around 260 pm to 740 pm, right? And the reactant molecules will get adsorbed, right? It will get adsorbed into these cavities or pores, right? So only the size of the pores generally varies, right? As I said, 260 to 740 pm. So only those molecules will be adsorbed in these pores whose size is small enough, right? So the molecules, right, or the reactant molecules that get adsorbed, right, into these pores, right, only those reactant molecules, right, depending on the size of these pores, only those reactant molecules would be able to adsorb into these pores that can easily enter into these pores and easily leave into these pores, right? Because when the reactant molecules will enter into these pores, right, it will react and form products. So the products should be able to leave the pores, right? So depending on the size of these pores, only those reactant molecules will get absorbed in these pores that can easily enter and leave the pores, right? So that is why, so it depends on the shape, right? It does depend on the shape of the reactant molecules, right? Which reactant molecules can get absorbed into these pores, right? If you take example of sodium aluminum silicate, right? The sodium aluminosilicate can absorb straight chain hydrocarbons, right, and not branched chain or aromatic hydrocarbons, right? So we say aluminosilicates can absorb only straight chain hydrocarbons, and not branched chains or aromatic hydrocarbons, right? Because the size of these sodium aluminum silicate, it's sodium aluminum silicates, the size of this sodium aluminum silicates, right, is such that the size of this sodium aluminum silicate is such that it can only absorb the size of the pores, the size of the pores which are on the surface of this sodium aluminum silicates, right? Those pores, right, can only absorb these straight chain hydrocarbons, right? The size is such that it would not be able to absorb the branched chain or the aromatic hydrocarbons, right? So now we understood what we mean by shape selective catalysis. That is why we call it as shape selective catalysis, because the adsorption of molecules depend on their shape, right? Why? Because these aluminosilicates, these silicates have pores, right, that have definite size, right? So depending on the size, right, depending on the size of the pores, only molecules of specific shape and size can enter into these pores, right? So that is why we call it as shape selective catalysis, right? And these are used, these catalysts are used in cracking of petroleum, right? And cracking of petroleum, it is used to convert alcohol into gasoline, right? So it converts alcohol directly into gasoline, right, by first dehydrating them, right, then so that a mixture of hydrocarbons is formed, right? So here this is just an example. Alcohols are it will first dehydrate them, right? These zeolites will dehydrate these alcohols and will convert into gasoline. This is it, right? And since the use of these zeolites as catalyst is only when water molecule is removed, right? So is there any use of these silicates in its hydrated form? Yes, there is. And these are used as ion exchangers in softening of water, right? In its hydrated form, right? In its hydrated form, or I'll just write it over here. These hydrated zeolites are used as ion exchangers in softening of hard water. Right? These are used as ion exchangers in softening of hard water, right? So these are used as ion exchangers in softening of hard water. So we have two uses now. One is as ion exchangers, and one we have already understood that these are used as catalysts, right? And their catalysis depends on the size of the reactant molecules, because only specific reactant molecules can get absorbed into the pores that are on the surface of these aluminosilicates, right? And these are stones, and this zeolites literally means in Greek language boiling stone. Why? Because the water molecule which is trapped in the pores of these aluminosilicates will start boiling when you heat this zeolite stone, right? And important is its structure. It's a honeycomb-like structure, right? Which has three dimension. It's a three-dimensional network silicate, right? In which some of the silicon atoms are replaced by aluminium atoms to form this framework of aluminium, oxygen, and silicon. This kind of framework is present in this structure, right? So I hope all this is clear to you. Thanks.